We have been taught that deeper is better for artificial intelligence, but new research from Meta and MIT suggests up to 50% of the layers in your state-of-the-art language model are redundant dead weight. In an era where GPU memory bandwidth limits inference speed more than raw compute power, adding depth often creates a bottleneck rather than improving capability. The most efficient architecture is not always the deepest one. Sometimes it is a single layer trained with massive parallelization that fits entirely in your video memory without swapping. This brief explains why shallow architectures can match full parameter training on specific hardware constraints and exactly when you should stop building deeper models to save money and latency. The theoretical foundation for deep networks comes from work by researchers at MIT's Center for Brains, Minds, and Machines, which established that deep networks are exponentially more efficient than shallow ones only for compositional functions where one operation feeds into another like language or vision. For these tasks, a single hidden layer would require an astronomically large number of parameters to achieve the same accuracy as a deep stack if you assume infinite hardware resources. However, this theoretical advantage ignores physical constraints that define modern engineering reality. Memory bandwidth and latency are often harder limits than raw parameter count. Contrary to theory, empirical studies on modern large language models reveal that current pre-training methods are inefficiently deep. Research from Meta, MIT, and Cisco found that up to 50% of the layers in popular open-weight models can be removed with minimal performance degradation on question-answering benchmarks. Layer similarity analysis shows that many deep blocks perform identical or near-identical transformations, acting as redundant stages rather than distinct feature extractors. This redundancy discovery means you have permission to simplify your stacks because removing these layers is a valid engineering optimization strategy, provided you apply parameter-efficient fine-tuning like QLOR with 4-bit quantization to heal the network afterward. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The shift towards single-layer or shallow models is driven by physical accelerator limits on GPU and TPU architecture rather than just algorithmic theory. End-to-end training creates an information bottleneck where intermediate layers differentiate roles too sharply, slowing down signal propagation in deep stacks on modern accelerators. Modern hardware favors massive parallelism over sequential depth because a single layer with high fan-out can be processed simultaneously across thousands of cores, whereas a 30-layer stack forces data to wait for each previous layer to finish. This creates significant inference latency. When you look at the trade-off, while deep networks are theoretically superior for complex compositional tasks, the engineering reality is that inference latency and memory bandwidth often trump raw parameter count. When a model fits entirely in high-bandwidth memory without swapping to slower system, a shallow architecture with massive parallelization outperforms a deeper stack on modern accelerators. This means you can successfully prune up to 50% of layers from models while maintaining performance, turning what was once seen as dead weight into a streamlined engine for production environments where speed matters more than theoretical depth. For the data engineer, this is a critical signal to stop assuming bigger is better as your default strategy for deployment. If you are deploying models on edge devices or cost-sensitive cloud instances where memory bandwidth is the bottleneck, aggressively pruning layers can yield faster inference and lower costs without sacrificing accuracy. For the AI practitioner, your intuition about depth equaling capability needs updating for production environments because current pre-training algorithms may not fully utilize deep stacks, leaving significant redundancy in your models. You have permission to simplify by removing redundant layers as a valid optimization strategy, provided you apply parameter-efficient fine-tuning post-pruning. The career shift here involves mastery, now involving knowing when depth fails. The ability to diagnose that my model is not fast enough because it is too deep for the memory bandwidth is a higher value skill than simply stacking more layers and hoping compute catches up. You should use depth for complex novel tasks where you have infinite compute, but switch to shallow single-layer parallelization whenever latency and memory bandwidth dictate your success in real-world applications. The data shows that researchers commissioned to provide insights on why deep networks work found multiple papers addressing different facets of this challenge, confirming that the industry is moving toward efficiency over brute force scaling. This approach changes how you think about hardware choices from the practitioner perspective because it shifts focus away from raw parameter counts and toward architectural fit for specific accelerators. It validates a strategy where you might train with massive parallelization on modern chips to achieve results that previously required deeper stacks, fundamentally changing your engineering judgment when selecting models for deployment. The key is recognizing that redundancy exists in current systems and that healing the network through fine-tuning allows you to recover capacity while gaining significant speed improvements from reduced sequential dependencies. The research confirms that up to 50% pruning is viable with minimal degradation on question-answering benchmarks, proving that shallow architectures can recover lost capacity if optimized for hardware efficiency rather than theoretical depth alone. This insight moves the discussion from abstract math to concrete hardware benchmarks where you see real-world performance gains when models fit entirely in video memory without swapping. The ability to diagnose bandwidth bottlenecks and apply pruning strategies is now a core competency for engineers who want to build systems that run reliably at scale without breaking their budgets or latency targets. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.